Okay, so I'm going to start off with method one. Method one is saying start the platform rotating and let it rotate freely. Use a feasible method for measuring the angular velocity at 2 different times. So I'm going to be kind of skipping around here, but this is really us figuring out a way where we want to know the frictional torque. So that's really just a torque that is happening because of friction. So it's just a torque. So it's us saying, well, the torque is equal to our rotational inertia, which we know, according to our problem statement, times alpha. And this is them saying, well, you can figure out alpha. You know that your alpha is your change in angular velocity over your time. So if you're able to measure the angular velocity at one time, and then at another time, and then know those times, you're able to figure out the angular acceleration, and then plug the angular acceleration to this equation where you know I, and then that will tell you the frictional torque, how much torque is happening. So that's what we're looking at in this case. So if your procedure had something to do with this, then you are good to go. So with this, I think collecting the data and thinking of ways to actually measure angular velocity, I think that that's very, very tricky. So we're thinking about, we want to find this change in angular velocity, and part I is asking us what quantities do we want to measure. So when I was doing this, when I was first setting this up, instantly my mind was like, oh, well, I can think about using one of these rotational velocity sensors, one of these rotary motion sensors that we used in class. The problem with this, though, is when we attach this to our disk, it's no longer freely rotating. So it's no longer just rotating and the only torque acting on it is friction. We would have a lot of torque acting on this and a lot of just like friction in general, a lot of problems with this, because this would be grinding up against our disk, right? If we like put it down here, it would be interfering with it, and that would be an issue. That would introduce this situation where we have more than one force acting on it. And that's not what we want in this case. We just want this to be freely rotating. So that may not be our best bet. So we need other ways where we can measure our angular velocity at some times. So one thing that I was thinking of, and you may have done this different ways, but that's totally, like, as long as you're able to come up with a sensible way of measuring this quantity, you're good to go. So one thing that I was thinking of is that we could figure out and say, well, we know that this V is equal to omega R, right, based on those previous equations that we looked at. So you can say this velocity is equal to our rotational velocity times R. We could say, well, let's put some sort of object, some sort of like small object at the edge of our disk. Okay, so we'll take a meter stick and we will measure R. I want to measure, what's this radius? Oops, I missed it. So R, I'm going to put it in a box and say, hey, this is something that we are able to measure. So I can say, well, let's measure this R. And then maybe we, I don't know, we could do a lot of things. Maybe we take a slow motion video. We put a little object here, like a small, let's call it massless object. And maybe we take a video camera and we put it above. This is a terrible video camera. But we take a slow motion video and we are able to then count, hey, how many radians, like look at every one rotation, say, oh, this thing is moving 2 pi radians, and it's doing it every some amount of time. So we'd be able to count then frames or look at this video data, and we'd be able to get time data. And that is one way that we could do this. We could figure out our rotational velocity by doing radians and measuring time. Sorry, I kind of went on a little tangent there that we didn't need to. Another thing I was thinking of is we could put maybe like a motion detector here, right? One of our blue motion detectors, I won't make it blue, and kind of set it up perpendicular so that every time this little dot passes through, it would show us a change in the position of our object. If we had that position versus time graph, it would look, oh, okay, we're very far away, and then when this little object passes through it, it would actually be more gradual, but it would look like, hey, we're close now, so farther away, close, far away, and we'd be able to count, oh, how often is that happening? How often are we getting this one full rotation? So actually we don't need this, v equals 2 pi r. But that is one way that we can do it, and that's kind of this slow motion video approach. That's the way that I'm going to go about this. I'm going to say doing it that way. Let me just read this really quick. All right, cool. So yeah, so that's going to be my approach. I'm going to look at 2 different rotations, measure how long that takes, and then go from there. So in this case, the quantities I'm going to measure is I'm going to measure the radius of the disk, and I'm also going to measure time. So those are really my 2 quantities. I just want radius and I want the time. But why do I want the radius? I actually don't. My bad. I just want to measure time actually. Right, that's really the only thing because we know that this is 2 pi radians. I guess technically I'm measuring the amount of radians, but if I'm doing a slow motion video, alright, what equipment would be used for the measurements and how would that equipment be used? So if we're looking at our key over here, part I is saying, okay, indicate valid measured quantities, so that's okay, I've done that already. And then we're going to get a point if we list the equipment in a plausible way to measure the quantities. So here's my things that I want to measure. Now I just need to set up a plausible way of measuring those. So I need to just, as long as I say this is what I'm measuring and this is how I'm going to do it, then I'm good to go. So I want to measure radians. And not so much measure, but just really count radians. So maybe I'll use slow motion footage. So slow motion video camera. Same way with time. And then I'm going to put like a reference point on the disk. And usually this is going to be a lot more straightforward. I think that this is frankly a confusing situation, so sorry for giving it to you. So I'm going to put some sort of reference point, a reference line on the disk, and every time it passes, I will just count how much time. So frame/time analysis of video. Okay, cool. Now I just need to describe the way that I'm going to do this. So let's go through it step by step. And really when we're thinking about what we need here, if we look at the key, all that we need for this part is we need a practical procedure that's consistent with AI. We need a plausible procedure that could be done. And then we need to include a valid method to reduce experimental uncertainty. So just say like, hey, let's do a few trials. So as long as our procedure is consistent with what we said we're going to measure, we are able to get points. So let's do it. So step 1, I'm going to say, let's put a, actually, I think I'm going to type this out. So sorry, it's going to change really quick. Okay, so let me, how do I type? Okay, so step 1, I'm going to say place a slow motion camera above the disk so that the whole disk is visible. And then I'm going to, so I've set up the camera so it's above the disk, place a small piece of, or maybe like a dot, place a small dot on the edge of the disk at one location. So this will be my way of keeping track of how many times it's rotated. And then I'll say spin the disk up to a top speed. And then I will say record on the camera once the disk has reached its top speed. And then I will record until the disk has stopped. Then we'll analyze 2 rotations using the dot that we placed as a reference for a full rotation. So check and see, and then I will pull time data from the video analysis software to see how much time a full rotation takes. Cool, so I'm going to say maybe, yeah. All right, so that's a procedure. Maybe it's not the best procedure, but it does everything that we need. Oh, and then I'm going to say, sorry, it hasn't quite done everything we need. Perform 3 trials. I know, let's do it 5 times. We don't actually have to do this. 5 trials to cut down on experimental error. All right, great. So we have cut down on our experimental error. And let's see, I want to move this over here so that we can match it up. All right, so if we look at what we needed, we need a practical procedure that's consistent with the quantities we measured. That's good to go. We only use the tools that we said we could do in parts AI. For a plausible procedure that could be used to experimentally determine frictional torque, yeah, that'll give us, before we have that equation, this will give us everything that we need. And then for a valid method to reduce experimental uncertainty, which we said that we did. So we are good to go. We have referenced everything that we have, and that's really all that we need. So then describe how the data from these measurements could be used to analyze and determine the frictional torque exerted on the rotating platform. So this one we're going to get points for a valid expression involving the necessary angular quantity consistent with the procedure in part A, for explicitly or implicitly relating the calculated quantity to angular acceleration, and then for correctly combining the above 2 concepts in a way that would yield the frictional torque. All right, so I did that math earlier, but I'm going to do it one more time. So in this case, we're saying we want to figure out this torque. And we know that the torque, the net torque, is equal to I times alpha. So we know alpha. So what we could do, we would have to say some sort of statement of use the time of rotation 1 so we pick our first rotation to find omega 1 by doing omega equals 2 pi divided by time 1. So we said before we would measure this time data for 1 rotation. So this is how we are calculating omega 1. Then we'd also say use time of rotation 2 to find omega 2 by doing omega 2 equals 2 pi over time 2. So that's us using our data from our experiment. Then we could say is, well, alpha is equal to our change in omega over change in time. So you can say omega 1 minus omega 2. And we have that time data from our slow motion camera. So we'd find alpha, we'd say torque is equal to I times, all right, and when we plug that in, we would get an equation for this frictional torque. So that's really all that we have to do for that one. We've said how we're going to get this, and then we will, we could plug that in and figure out the frictional torque. So that should, we've related to angular acceleration, and we have included our quantities, and then we put it all together. So in this case, does the experimental procedure in parts A and B depend on the assumption that the frictional torque is independent of the platform's angular speed? So in this case, we have a yes or no question where we want to say, where we're thinking about our experiment, did it depend on the angular speed of our platform? And in our case, yeah, it did. We based our whole entire analysis on the angular velocity of our disk. So if our angular velocity changed, our data would change, right? Over here, our angular velocity is based on our angular speed. So it really all depends on the angular speed. So we did make that assumption. Which part of your analysis depends on this assumption? The part where we measured angular velocity. So our data was from angular velocity. In this case, they want us saying we really just get points for quickly relating the procedures in part A and B to the assumption of dependence. So yeah, we said, hey, it does depend on it. And then for analyzing the dependence of it, so just saying we measured the data over t, which is equal to our angular velocity. So it depended on angular velocity. If you answer no, we did not answer no. And then this last part, just kind of modify what we could do to determine whether or not this is speed dependent. So in this case, we do need to make a modification. And really what we could do is just do it again, experiment again, at different speeds. And this will tell us, hey, if our friction is changing, then we know that it is dependent on speed. If it doesn't change, then we know that it is not dependent on speed. So in this case, they're saying for modification that has any additional trial at a different angular speed or states that none is necessary. In this case, we are doing it at a different speed. Analysis of the initial or modified experiment could plausibly determine if it is independent. So do it again at different speeds, and then we would just check to see if our frictional torque data is equal or not equal to previous trials. And then we'll just say if not equal, then it is dependent on angular speed. Oh my god. Alright, so that was kind of lengthy, sorry about that. But hopefully that was helpful. And yeah, that was our method 1. So hopefully that was kind of helpful. It's definitely helpful to see those keys for me to see like what the College Board is looking for. And yeah, that was a lot, but thanks for sticking with it. All right.